All right. Good afternoon and welcome to the Transportation Infrastructure Durability Center's March webinar on improved helical pile performance with collar vane technology. My name is Aaron Schanck, Communications Specialist for the TIDC, and I will be moderating today's event. The Transportation Infrastructure Durability Center is the 2018 U.S. DOT Region 1 University Transportation Center located at the University of Maine Advanced Structures and Composites Center. TIDC's focus is on extending the life and improving the durability of transportation assets through 4 research thrusts: advanced structural and performance assessment, development and implementation of novel materials, advanced structural systems and applications, and advanced performance through innovations in safety, resilience, and connectivity. TIDC has 6 member universities within the New England region: the University of Maine, the University of Connecticut, the University of Vermont, the University of Massachusetts Lowell, Western New England University, and the University of Rhode Island. Today's webinar will consist of a 40-minute presentation followed by a Q&A session. During the presentation, please use Zoom's Q&A feature for any questions you have for our presenter, and we will go down the list in our Q&A session. If we don't get through them all during the scheduled time, there will be a link at the end of the webinar to submit any further questions, and we'll email you a follow-up. Our presenter today is Dr. Aaron Gallant. Dr. Gallant is an associate professor of civil and environmental engineering at the University of Maine and a research lead for the TIDC. He earned his bachelor's in civil engineering from Tufts University and went on to pursue his master's and PhD in civil engineering from Northwestern University, specializing in geotechnical engineering. His research interests lay in combining theory and practice to reconcile observed performance and behavior of natural landforms, geomaterials, and subsurface infrastructure, with emerging interest on ground improvement stabilization, behavior of gassy unsaturated sediments, and resiliency to instabilities during extreme events and dynamic loading, and soil structure interaction. He previously worked as a geotechnical engineer at CH2M Hill in Virginia before coming to teach in the Civil and Environmental Engineering Department at the University of Maine in 2016. He is a member of the American Society of Civil Engineers, the Deep Foundations Institute, and the U.S. Universities Council on Geotechnical Engineering Research. So, without further ado, the floor is yours, Aaron.
Thanks, Aaron. Appreciate it. Let's see here. Could you just confirm for me quickly, Aaron, that you can see the slide? I got a thumbs up. Excellent. All right. Welcome everyone to the webinar today. I'm really pleased that you all took the time here joining us for our lunch hour. As Aaron mentioned, really, I'm going to be discussing today or presenting on the development really of a collar vane, which a concept that was invented to really enhance the lateral and torsional performance of helical piles. There's a lot of folks that have contributed to this project. Certainly, the graduate students, I'd like to mention real briefly Juan Sebastian Carvajal Munoz, who was our first grad student on the project, and our second student now, Camilo Fernandez. They've done a lot of fieldwork analysis and certainly contributed to the project. We also have other faculty members that are part of TIDC, Aaron Bradshaw from the University of Rhode Island, and Keith Barabee from the University of Maine. We have an excellent partner in this project from Hubbell Power System, in Hubbell Power Systems. And certainly some folks that I'd like to mention would be Gary Seider, Sean Downey, Ben Jennings, and others that have really contributed to a lot of the field work and field testing that you'll see today. So it's a big group. It wouldn't be possible without any of the characters that we see named here. And so I just want to make sure that they're not part of the line. Quick idea here, just to kind of set the stage, is really we want to think about the United States Department of Transportation goals for the University Transportation Center program. which really funded a lot of this work. So that's what TIDC is. It's one of the regional UTCs in England. And the goals of this program are really to advance or develop, emerging technologies. And so certainly that's what today's webinar is focused on, but also enabling technology transfer and deployment, right, to benefit and achieve, desired outcomes in transportation. And so that was one of our goals here. And so one of the things that certainly we want to recognize here is that our close relationship with the New England DOTs, in hopes of, for things that come out of this center, the work that comes out of the center, so we can hopefully transfer that knowledge and technology moving forward. And not just in transportation, but in certain other fields or industries as well. Where I'd like to start today is when we thought about enhancing really the lateral performance of helical piles, from a transportation perspective, we started thinking of sides. And really, what were the typical details, which are or typical foundation details that you'll hear used, or that's terminology used inside departments of transportation. And when you start looking at them for typical sign instructions, they're all pretty similar for similar sign sizes, as to be expected. Generally, these are foundations expected to be 18 to 36 inches in diameter, typically concrete, all right, with some steel reinforcement. Generally speaking, you'd expect them to be embedded anywhere from 5 to 8 feet in the ground, really depending on side height and area. So these are typical details. They work well, they perform well. We don't see a lot of signs falling down. But we're hoping here that the technology that we've been trying to develop here over the course over the last few years will add really another tool to the toolbox for DOTs and others. So one of the reasons that we would really want to think about potentially using helical piles is really the rate and ease of installation is often greater. All right. If we go ahead and we think about a conventional concrete base, you've got to drill a hole, you've got to pour concrete, you've got to add some sort of steel reinforcement, you've got to have a base plate, all right, and two hooks that basically connect up. All right, and this is a lot of time. All right, the installation of these foundation elements are not quick. What you see going on in the video over here next to me, all right, is the installation of the helical pile. You see the helices and lead extension going in the ground, and this kind of gives you an idea of how quickly, all right, these can be installed. All right, so that's certainly one advantage and one of the things that we'd like to take advantage of when we enhance this foundation type. Okay. Another thing that is worth noting is that this can also be retracted and taken out of the ground. So there is also the potential for foundation reuse, say if you want to move one of these side structures. Okay. So we kind of came up with an idea as we were sitting there during the pandemic. It was March, April 2020. I was sitting on the phone with Hubbell Power Systems and another distributor here in Maine, and we started talking about ways that we could come up with a way to enhance the lateral capacity of helical piles. And really what we came up with was this idea of a collar vane. And that's what you see down here in this bottom left-hand corner. So this is kind of the ideation process when we're talking about, development of technologies. You got to kind of get an idea right here. It's intended to sit at the top of the pile. And when it's in the ground, you can kind of see the tops of it right here in this top right-hand photo. All right, this is from some of our testing. So you can kind of see the helical lead extensions, and this is ultimately pulled in the ground. I'll touch on that a little bit more later. But one of the ideas that we wanted to do was we wanted to maintain a slender shaft, a slender pile. We wanted to minimize the amount of material that was needed. So we want to take advantage of the reaction that occurs near the top of the pile, which is generally speaking where most of the lateral resistance, whether it's torsion, okay, or lateral shear resistance is generated. It's up here at the top where you get the most movement. You have to have movement in order to generate resistance. You can think of the soil like a spring in that way. And so we said, why create a large diameter element the whole way through the ground when you really only need that large thing at the top? Additionally, we want to use this vane in such a way that we can keep the structural loads in this slender pile slender pile small. Okay, and so those are some of the things that I'll focus on today. So when we install this, okay, and I'm showing just a comparison now, and you'll see here, really we're going to extend our lead extensions. All right, we'll have our shaft that will extend through the collar. All right, as we apply torque and crowd, you'll see this flange will connect with this base plate. And as we do that, we're going to pull this thing into the ground. Once it's finally in the ground, we'll lock off the flange, all right, with the base plate right here, all right? You can kind of see a photo of that, so it's connected. Just to give you an idea of how quickly this can be installed, we're really not changing the process of installation. That was one of the things we were attempting to achieve. We wanted to keep the rate of installation high, all right? And so that's one thing that we were really focused on as we pursued this. So if we're in a situation where, you know, we have a relatively large soil column, we can pull this in the ground. So what you have is the lead extension and helices below actually pulling the vane into the ground, all in the same installation process. So this was our idea. We wanted to go out and test it. We wanted to see if we could make it work. And we wanted to see if it would perform similar to, say, typical details for the Maine DOT. So as you're thinking about advancement and development, you know, there's really, you know, the selection of ideas. You know, what are the good ideas? And you know, what do you actually pursue? And, you know, this is something we're faced with all the time here at TIDC, but just generally in industry and research process. So, you know, selection is, you know, can be driven by cost, you know, value engineering, you know, what resources do you have, the potential for the immediacy of impact, potential long-term benefits. We really saw ourselves as trying to really come up with something relatively quickly, you know, not something that was going to take decades to develop. You know, feasibility, you know, what is the potential for success? Will it work? You know, the durability and resilience. And then decision makers and potential adopters, right? Finding early adopters early on who might benefit from this is always important in this advancement and development stage of technology development. And then the ability to investigate. And so right here is where I'll highlight our partner in Hubbell. They really provided us with the resources, personnel, you know, equipment, in-kind support that was needed to do the field work to really investigate whether or not this would be good. Not to mention, you know, they also manufactured everything that you'll see in our presentation here today. So, and really what this results in is really some testing and refinement. So you start off and you start trying to think about what worked well, what did we learn, is refinement warranted? And, you know, you crank out, you know, a subset of good ideas that might not have worked. It doesn't mean they were bad ideas, but they may not have worked the way you thought. And then you often find a subset of ideas here that really work well. And you know, generally speaking, this can be demonstrated through, and this is general, not necessarily in our case, but bench scale testing. We're going to do a lot of this. Then scale into in situ or field testing. You'll see a lot of this here today, modeling, and really ultimately coming up with an engineering approach. You've got to be able to describe how this will work. All right. And then, of course, publications can kind of help with acceptance. So, what we've been up to here the last 3 summers is focused on testing, okay? In summer 2021, 2022, we had one graduate student out there for the first time installing a vane with Hubbell and performing lateral and torsional load tests, okay? Next, we tried to move out into the field and we started focusing on a new way of testing these, in that we actually wanted to simulate more faithfully the loads that are applied to sign structures. This was going to be our way of demonstrating to folks that, you know, these have the potential to work for signs where you have applied shear and large moments. Okay. We've also performed some pushing tests here to understand the vertical resistance that these vanes can that these vanes generate as well. There are several modes for that I'll get into going forward. Where did we test? We tested at Hubbell headquarters in Missouri. So the last 3 summers, we've been heading to Centralia. All right, this is near Columbia in Missouri. All right, for several weeks at a time. I'm showing a close in here of Centralia, and Hubbell certainly has a large footprint in this town. You'll see here they have a dedicated research center, certainly distribution, even a composite center. I'll mention that later. Manufacturing and corporate offices, and then you'll see our test site right here I'm going to hone in on this area, the test site next. It's really a greenfield site that provided us some room to work. What you're looking at first here is kind of a staging area, a clay testing area that we looked at. All right, most of this is clay, and then over here we have this sand testing area. So we tested in 2 soil types. We thought that was important. This sand, of course, this sand did not exist initially, right? Hubbell certainly invested substantial resources in developing really what was a sand pit. All right, so that we could test this product in sand as well. Something we really want to demonstrate to potential users. Okay. So with that, we've performed, pretty thorough subsurface investigation at these sites, including, cone penetration testing throughout the area. So the site is really well characterized. Okay. If we move into the characterization here, we're really worried about the upper meter. Okay. I'm showing you results from cone penetration tests. And what we typically have here is a desiccated or a heavily over-consolidated clay here on top. That's very common for one of these sites. You see the water contents here and closer to plastic in a particular case. Here I'm showing some undrained shear strengths, both residual undrained shear strengths interpreted from the CPT, peak shear strengths, and then also results from unconfined compressive tests and Vane shear tests. But give you an idea here of the shear strength expected. Again, we're focused up here at the top of the column. Okay, so generally a clay, silty clay is what we're dealing with. Okay, naturally. Now, if we go inside the pit, you'll see that this pit was essentially 3 meters deep, or close to 3 meters deep. Here, where you see this increase in tip resistance up high, this is that sand pit. All right, we dimension penetrate through. Okay, so just this is kind of the subsurface conditions that we're dealing with in the sand. All right, and I would say it's a medium dense sand. It is what was ultimately prepared. So now let's get into some of the results, the testing that we did. What you'll see here is we have a setup here for torsion. This is relatively unique. You'll see here that we have this moment arm, moment frame, torque frame, if you will, 2 cylinders, all right, hydraulic cylinders here that pull on that to create a couple, all right, string pots that are measuring deformations and rotation. All right, and then also this vane, or excuse me, the shaft is outfitted with strain gauges as well. We really want to monitor the moments being applied. So here's kind of a plan view of what that looks like. Again, we'll pull this direction, we'll pull this direction to apply some torque. I've never seen this before, and I think you'll find this relatively. Here's the controller that we use to control those loads. I'm not going to go into how the controller works. That's not the point of this slide. This is what's governing, okay, or how we have steady control. This is just a neat video that you'll see here afterwards. In geotech, we're not often seeing what's going on above the ground, but here you can see how we can push and pull on that vane. All right. What I'm illustrating here is a particular case where we were performing a cyclic load test. So we actually applied over 1,000 loading cycles during this particular test. But the video certainly demonstrates kind of how this system works. If we get into some of the results, we've got a lot of tests, but these are very representative of what you'll find, particularly in the clay. Here down below, you'll see in this solid line with no symbols, this is kind of the torque that you would expect, all right, with no helical pot, all right, or the torsional resistance that was applied. And it's certainly here is the diameter or height, all right. Basically, when I'm talking height, the height of the prismatic section of this collar vane increases. The torsional resistance also increases. So we're showing here the torsional resistance and that angle of twist, okay, or rotation that we're getting at the pile head, okay? So as expected, the collar vane is substantially increasing the torsional resistance. That's no surprise, okay? Here you kind of saw that opening slide. Here's a full picture of that. This is in the sand. It's a little cleaner to look at, but you can clearly see here that it looks like we're creating a torsional or cylindrical, excuse me, shear surface, okay? And here's something coming out of the clay. So really you can see the perimeter of the vein. We're really mobilizing shear resistance along the perimeter of the vein, but also up top. If you are a geotechnical engineer, you can really think of this just something akin to the field vein test, right? It's effectively a field vein around the helical pile. Couple of things that you want to be careful of here is thinking about, all right, how you mobilize the resistance, all right, at different strain levels. Okay, are you at, what strain level are you at? We're not mobilizing shear strength along this cylindrical shear surface uniformly. We were in a dense clay, and we were just interested here in what methods to estimate, shear strength around the cylindrical shear surface worked best. You don't need to, I'm going to explain this in more general terms because we have a broad audience here, but what you see over here is we're looking at the predicted capacity for different shear strengths with the measured capacity and the design method. So if we were to, for example, use peak shear strengths from the field vein or CPT, we would way over predict the capacity, okay? If we move over here to alpha methods, where we're really effectively looking at a residual shear strength, all right, something way out at the end of a stress strain curve is effectively what you're looking at. We tend to more closely predict what that capacity is. So these are really residual shear strengths associated with either CPT methods or other alpha methods, okay? And so our grouping here suggests that, okay, we're really looking at a residual shear strength. Right, that's effectively what this slide is telling you. We also performed lateral load tests. Okay, you can see the pile here. We're going to go ahead and have a reaction pile in the ground, and then with the cylinders, we're going to pull on this and measure the load displacement and structural loads in the pile itself. All right, let's see how it helps us there. All right, if we go ahead and really what we found, but not unexpectedly, is that the collar vein substantially increases the lateral resistance. All right, so if we look at the applied load and deflection at the pile head, as we increase basically the diameter, which is the black lines and the highest diameter, in this case, 0.9 meter or 3 foot diameter section, 2 foot section, the blue lines, 1 foot section, the red lines, as you move across the family of curves for different colors, that's just the height of the pile increasing. So really just basically what you expect. And just to give you a reference point here, this is the lateral resistance for the case with no vein. So as we continue to increase the diameter of the vein, height, as we move across this family of curves here, all right, we look at the ratio of applied load with and without the vein, all right, we're upwards of 20 plus times resistance, all right, for larger vein diameter. So that's significant. All right. And this was evaluated at 10 millimeters, so less than half. It's relatively small. The vein has also been designed here with a unique load transfer mechanism. All right. So what we've been talking about before was really a geotechnical perspective, but how are we keeping the loads low in the pile as well? Well, the vein has an annulus around, all right, the inner shaft. And so as we mobilize geotechnical resistance along the depth of the vein, it all gets transferred, all that resistance gets transferred up through this flange at the top, structurally connected. Okay. So really, we're not transferring any load through the vein section. We're mobilizing resistance for the vein, but we're not transferring it to the pile shaft, except up here through the flange, which is where the shaft of the pile and the vein are connected. All right. And so what you would expect is to have a constant shear in the pile. All right. And if we go ahead and look at the moment versus depth over here in the right-hand plot, the fact that this moment increases at a constant rate does indicate that we have constant shear. All right. And that really we're not interacting, all right, with the pile. All right. Or the vein itself isn't interacting. The collar of the vein is interacting with the pile along where it is. Okay. And so we go ahead here and we look up at the top of the pile. We do have some constant shear in there, but the other big thing is that the moment is very low at the pile head, all right, which is implying that we're mobilizing most of the resistance up here or an equivalent load equal to what's applied and transferring it back, okay? If you look at the moment values that you would expect for this pure lateral test here, they're much greater at the pile head if there was no vein, And we've confirmed that's the case when we have tests without a vane. All right, so this is absolutely the case. All right, so really protecting the load. This is keeping the loads low, below the yield strength. All right, which in this case, to about 12 kilograms. If we want to think about the amount of resistance we're generating with the vane relative to the load that's applied, so VR being the vane resistance that's being generated, normalized by the load that's applied, you can see here at small deformations, we're anywhere between 100%, all right, to 80% or 85%. As the load increases or deflections increase, okay, this percentage tends to decrease to some extent. It tends to decrease to some extent, right? But by and large, the majority of resistance that's generated from a geotechnical perspective is by the vane tests. Okay? If you're a geotechnical engineer, you might be thinking of this, from a finite element or finite difference where we perform a PY analysis. Now, for a pure pile, we can think of the soil along there as being a series of springs, all right, with available resistance, that's dependent on the deformation. This is something that's performed every day in practice. Now, when we have the vane, we have to kind of separate, all right, the idea of the generation of resistance from the vane to that that's generated by the pile. So what the vane is effectively doing, if you want to think about this from a PY analysis perspective, all right, is we're effectively concentrating all the resistance from the vane up top. All right, so we really need to come up with basically a PY curve for vane, all right, which we've been looking at, and there is some rotational resistance as well. Okay, there's also a percentage that might get applied, all right here at the bottom, and we might get some contact. All right, there is some contact that might occur right at this location. So these brown springs that you see here are really meant to represent the forces that are ultimately being applied, or effective springs that are being applied to the shaft to help keep those moments low. And with a conventional PY analysis, this is just to kind of give you an idea. As long as we maintain compatibility of the deformations at the pile head, all right, with that of the vane, all right, and assume that the vane is rigid, if that's where we started with, all right, you'll see that we can reasonably predict the pile head deflections with load. You'll see the moment profiles at different load levels. Basically, the applied load and moment is increasing as we go across this one curves, where the lines are the predictions and the symbols that you see here in dashed lines are measurements. So we can reasonably predict those things. And if we think about this coefficient C here, which I haven't defined, but it's effectively or very similar to really the ratio of this this vane resistance that we're generating up at the top of the pile relative to the load, we see it decreasing in a very similar fashion, or predicting that it decreases in a very similar fashion, similar to what we interpret from the field test results. Right? So not sure, but that might give some folks a visual of how you can do this from an analysis perspective, and we're still fine-tuning that for folks. So what I'd like to do here is kind of switch gears and really get into this last summer's or summer 2023's testing by first talking about sign structures and really the fact that loads are primarily a function of wind speed and the area of the sign. These are the largest loads that you'd expect to find on sign structures. All right. What I'm showing here in this particular table, all right, are the typical, all right, details or foundation details presented by the Maine DOT. As I mentioned earlier, all states tend to have a similar typical detail, all right, for single support signs and multiple support signs. What we went out this summer and intended to do was to look at, their 18 to 24 inch diameter concrete shafts, really, that they designate for different sign sizes, all right. And what we focused on here was the largest sign size in this particular category, all right, for these type 1, what I consider type 1 signs by the Maine DOT, which has an area less than 42 square feet, okay? The maximum height, all right, would be 12 feet to the center of the sign in this particular case. So I'm showing here a wind speed equation. We're effectively going to evaluate the loads by applying really a wind speed against, all right, wind pressure against this area, all right, during the sign. So when we went through and evaluated the loads here, we looked at different sign panel areas. Here I'm showing meters squared, all right. But out here, right around 3.9 meters squared, that's that 42 square feet, or that largest of the type 1 sign structures that I mentioned before. And we evaluated really the torsion that we could expect to be applied, which is primarily a function of the assumed eccentricity or offset here. And we just went by the design code here to come up with some estimates, all right. And if we look at that, the sign panel area for even the largest wind loads typically applied, we might be upwards of 2.5, all right, kilonewton meters, all right. So I just want to demonstrate here, at least for a single post sign structure, when we're thinking about torsion, well, the torsion that we expect to be applied would be these red lines that you see right here, all right. Something very low relative to the amount of torsion resistance that we have demonstrated we can generate in the field. Okay, so that's something worth noting here. So when we're thinking about these single post sign structures or type 1 sign structure class, we've got plenty of torsion resistance, and we can anticipate that would be the case. Okay. But the next point, and this is something where the moment frame comes into place that I'm going to show here subsequently, is we wanted to see how the vane would handle really that combined overturning load as well. All right, so really we've got a sign structure up in the air. It's going to have a wind load. If you pay attention over here in this bottom right figure, it's going to have a wind load coming in. That pressure and ultimate force that's applied at this location will result in an overturning moment right here down at the base, right at the foundation. Okay, and we wanted to be able to simulate this combined shear, all right, and overturning moment for the largest sign area, okay, this 42 square feet that I mentioned before, which is this location, and the highest wind speeds. So this is what we targeted in our testing, all right, and this is what you'll see moving forward. So we came up with a relatively unique, okay, experimental setup and load frame. What you're seeing here, this triangle, all right, is our what we call our moment load frame. Okay, what we're doing is applying a vertical load, all right, out here at the end, all right, where we're going to go ahead and create a moment, all right. But what we're doing with this diagonal member here is we're attempting to take any shear or lateral force out before we hit the pile head right here at this location. We wanted to independently, okay, control the shear. So we have another load cell, all right, or excuse me, another cylinder right here, a load cell where we control the shear, which is going to be constant, all right, which we'd expect to be constant, all right, in analysis. Now, by increasing the load here, we are effectively increasing the moment or raising the sign. Okay, so if we go back to this previous picture, all right, what we're doing is simulating this approximately 6 kilonewtons of shear force. And then as we increase the moment, what we're effectively doing is increasing the height of the sign or increasing the moment, okay? Increasing the moment as we increase the height of the sign. So we went up to the highest, all right, sign height specified for that type of detail. All right, that was kind of our baseline, right? We want to make sure that the moment frame worked as expected. So we didn't use a vane at first. All right, went ahead and applied some loads. We're looking at the theoretical moment and measured moment, and with strain gauges on the pile. And certainly we're hitting basically that 1-to-1 line. So we felt very confident we were doing what we expected. So it's just proof of concept there. What we'll do is we basically get the pile in the ground. These cables that you see sticking out, these are for strain gauges on the pile itself. We've got the vane in, you see the flanges locked off here, and then we've got a conventional base plate that really the moment frame is connected to. All right, so you can expect that this pile head and vane is going to rotate the same as this base plate. So what did we say? What did we see? Well, preliminary results indicate basically the load transfer mechanism is still very beneficial with this configuration. So what I'm showing here is applied moment at the head. All right, the black lines are with collar vane. All right, different size collar vanes. And the red line is without, right? See that the moment is higher. But what I want to bring you in here, and what I really want to highlight is bring your attention up here to the top of this diagram. So I'm going to blow it up. Look at the moment that we're applying, right? We expect the moment with no collar vein to basically be the same as what's applied, similar, and that's what we're showing here. The applied moment at the pile head for those other cases with the collar vein, even though the moment is lower in the shaft, all right, we're applying a much larger moment, all right, up at the top, all right? And that's because of the way the vein is interacting with the shaft, all right, and basically adding that rotational restraint, all right? So basically keeping the structural loads and stresses in the pile very low. And this is a really important concept. This is one of the unique aspects of the pile. One thing, and this was in discussions that we had with the DOT, okay, after one of our first summers of testing, was really just trying to have some comparisons. Well, number one, can we actually simulate the exact loading that we expect, all right, for sign structures, which I just presented in the last two slides, but also would we have a direct comparison with, say, typical details, all right, for the DOT. So what we did was we did in the clay and the sand, we constructed, all right, some shafts, all right, some 18 and 24-inch concrete shafts. We used some steel reinforcement, all right. In this particular case, it was a larger steel section that with a base plate that Hubbell had on hand. So that's what we used, tensile reinforcement there. But we're going to get the geotechnical resistance that you expect from a 24 or 18-inch diameter. Typical detail, which is what I mentioned before. So that was our motivation for going ahead and testing these. If we go ahead and we look at the field test results, really they're indicating that the collar vein system can support sign structures, number one, but has comparable performance to the typical detail. So I'm going to go into this just a little bit. Over here on the left-hand side, these were tests performed in clay. Over on the right-hand side, you're seeing tests performed in sand. And on the vertical axis of both these plots, you're seeing the applied moment and then the pile head deflection. Okay. The open symbols are collar veins. Okay. The open symbols that you see here are three, where the first number is the diameter of the vein in feet. And basically the second number is the height, the thickness of the prismatic section of the vein, all right, in feet as well, right? Not in meters, okay? And then the closed symbols that you see, or gray symbols, are the results from typical details, either 18 or 24-inch, all right, concrete shafts and sand and clay. And you can see here that we're getting similar performance with the collar vein as we did with the typical details. And so that was very encouraging. The red line that you see down here, all right, is the case with no collar vein. The color bands that you're seeing, these are the applied moments that are equivalent to different wind speeds, all right? So these are the applied moments that, you know, are for the red being the largest wind speed typically used in design, all right, close to that. And the different wind speeds are really what you're looking at there with those color bands. So as long as we're exceeding, all right, the resistance, all right, required at this wind speed, we should feel pretty confident in a similar way. These are adequate, okay, for at least what's considered in design, right? Most recently, we also went ahead and performed some push-in tests to really understand the vertical forces that we were overcoming. If over here on the right, you're kind of taking a look or a video at these push-in tests, with a hydraulic cylinder. I've sped it up by 16 times. But we wanted to understand, number one, what vertical resistance does the vane have on its own? Okay, what vertical resistance does the vane have on its own? We wanted to understand what kind of pull-in forces would be required. All right, so this summer, we're attempting to go out and actually perform some more installation tests where we're trying to look at, you know, how long do our helical piles need to be to pull it around. And the third reason we looked at this is a potential way to install the vane also, where you just have your helical pile. You could use a shorter helical pile potentially, use it as a react off it, all right, push it in the ground, and then just finish off and screw the rest of the helical pile down. So there are kind of three motives there for looking at this and we're kind of steps. Some typical results here, as you'd expect. The amount of embedded length that we have, the amount of embedment, basically the depth of installation, if the applied forces go up, The darker symbols are 3-foot diameter veins. Open symbols are 2-foot diameter. Similar thing here in both clay and sand. Shown here in kilonewtons, anywhere from 150 to basically 250 kilonewtons might be expected. If you're trying to relate this to tons, this is probably anywhere from 35 to 55 tons, all right, of vertical force required to keep moving this man. So generally quite a bit of resistance. Down here at the bottom, this is for another discussion. This is really some precipitation that was going on. We had a relatively dry point in the summer. We were trying to explain what was going on with this particular test that showed a different response. It was a relatively dry period. As soon as we had some precipitation, right here, that's this test. As soon as we had some precipitation, you see soften up that clay soil. Response or a similar response. So, where are we and what's next, really? Well, basically, the collar vane has been manufactured and really tested pretty rigorously over the course of 3 years. And we've shown that the collar vane, of course, substantially increases the lateral torsion capacity of helical piles. It also helps to substantially reduce the moments imposed on the shaft of the pile. So in other words, we can keep the shaft diameter small, right? We can keep a relatively small diameter shaft along most of the length of the pile when we just have this vane up top, all right, trying to optimize the material of that. And the other thing is that we've shown here in that last summer's testing is that it does provide adequate and comparable lateral performance to typical foundation details for sign structures. So we got adequate performance for sign structures, and it has a similar comparable performance to some typical foundation details for sign structures. And so that was really encouraging as we continue forward. And what's next? We're really looking for some industrial and DOT partners. We think we're at the point where we can start looking at low stakes projects, low stakes structures, things where installing these in the field and talking to contractors to see, is this a potentially good way for us to be supporting science, or a convenient way for us to be installing foundation or another foundation type. I think there are opportunities here to go out and demonstrate that this could work and add something else to the DOT's toolbox, contractors' toolbox, designers' toolboxes, and other industries. Okay, so we just kind of work together there moving forward. When we think about the technology transfer, this is kind of the last stage. Moving inventions and concepts and design techniques or constructive methods from really the creators to the public and private users. And so that's Maine and Hubbell trying to think about how we move this over. And then it is important to kind of understand the relationship here between creators and businesses and departments of transportation, which funded this particular research. Creators and businesses basically need to implement commercially. They got to find early adopters within a DOT or industry. And you need to get something contracted. And this is typically the hardest part. Okay. And DOTs demand competition, usually when you're going for contracting. And this is, of course, a good thing, right? This is to protect the public, right? They should protect the bids. There are non-competitive options when we're talking about new technology. You can specify new concepts, inventions, and methods, sole source demonstration project, or for experimental purposes. Okay, so this is one avenue that DOTs use, all right, to demonstrate new products. Okay, there are also other ways. This is the way that I see most likely to work. But there are also, product certification statements that could address, function. The product is necessary for continued operation, aesthetics, logistics. I don't think that this is probably something as applicable. Or public interest funding, such as cost effectiveness. Is another reason to go forward. That's still something, that needs to be worked out in large part, by our industry partner. So with that, I want to appreciate everyone for coming today, but first acknowledge, really that this funding was made possible, by the U.S. DOT and the University of Transportation Center program. But also in no short in no small way, the cooperation, kind of the exceptional cooperation and teamwork that the team I mentioned at the beginning of the presentations had with Hubbell. They're great. This is one of those dream products when dream projects when you kind of get to dream up an invention and you've got something there really live. And certainly this would provide a lot of support and resources to make this happen. So with that, I'd like to thank everyone for coming today. I really appreciate your attention and be happy to answer any questions that you might have. I'll also just note that Gary Seider here from Hubbell is also allowed in case he has anything. So thanks again.
Thank you very much, Aaron. That was a great presentation. I know I learned a lot about where the technology has come thus far and where it's going now. And we're going to open it up to Q&A here. We have a few already in the Q&A chat, but as more come in, I'm going to first ask what size installation machine is required for collar vanes, and what's the crew size like for that?
Aaron, you want me to take that one?
Sure can, Gary.
Yeah. That's a good question. What we as a crew, what we did with a lot of these installations, we used what we just had. We had digger derrick trucks. So you're talking 30 to 40,000 pound machines with 20,000 foot-pound torque motors. Some of the smaller vanes that Dr. Gallant showed you could be easily installed with a mini excavator. So, a 10,000 pound machine, 12,000 pound machine, that type of machine could be used. The bigger the vanes get, the bigger the machine is. The 3x3s are going to take a larger machine comparatively. So you're in that either a 20,000 to 30,000 pound excavator or a digger derrick truck for the larger ones. Crew sizes will be 2 to 3 guys. Obviously, the bigger vanes weigh more. So, and that's something we're actively working to change. Trying to reduce the weight of the collar vanes is something that we're actively working on as well.
Great. Thank you, Gary. Our first from the Q&A list, could you please comment on the friction between the soil and the vane structure? We'll send that over to Aaron.
Comment on the friction between the soil and the vane structure. I guess I'm not sure what you're referring to specifically. I mean, there's certainly friction developed. That's how you develop that frictional resistance or torsional resistance. That's through the shear strength. There is friction there. I'm not sure if maybe you were talking about the friction that develops between the top flange and the pile as it's being installed, in which case we've used a lubricant at that connection, basically to decrease some of that resistance that would be generated. But between the soil and the vane structure, there's that's what generates the geotechnical resistance.
Yeah, I think he may be referring to how much effort it takes to push the vanes in. Maybe in a more unit-wise, surface area type of analysis, I guess. Vane area.
To get them in the ground, yes, and that's where you see those push-in tests. We did have some results presented there where that's what you saw, I guess, at the end with those installation forces. And that's what we're working on in that regard. Yeah.
Do either of you have any concerns about near surface erosion or frost impacting the lateral resistance of the vane?
I'll start, Gary, and let you follow up. With respect to erosion or frost resistance, what you'd want to consider there is, well, if you're in a highly energetic environment, all right, a really water energetic environment where you expect erosion, this is probably not the most appropriate choice. it's, I wouldn't expect this to be used for a bridge pier or anything like that. With frost, what you'd be thinking about is really the thaw, any thaw or, frost or thaw weakening that might occur. Iceland's development and subsequent thaw weakening. In which case you would design, for that strength potentially. Those, a combination of those wind loads. Do I think that the frost is going to push this up out of the ground? The answer is no. You've got the helical pile deep that's restraining it vertically. The ground might move relative to the vane, but you're not going to have the sign coming up out of the ground. So I don't really have any concerns from that perspective. But if you're talking about the design strength of potential thaw weakening soil, that's something to consider. That would be true, but that would be true for any, but I'll just make the point here that is also true for any foundation, any drilled shaft or otherwise.
That I'll just add to that. I mean, Aaron already said it, but the helical pile itself is going to resist any uplift due to any frost heave that might occur within the area of the collar vane. But yeah.
Perfect. Here's a quick one for, we'll say you, Aaron. How is the vane connected to the helical pile?
The vane is connected to the helical pile through that flange, and it's possible that I went too quickly through that slide. I can try and bring it up quickly. And it wouldn't be unreasonable if I share, we can see what's going on here. You see this flange right here. This is what's rotating around the base plate. Once it's in the ground, you put in these bolts. And that's really how it's connected to the pile. So there's a flange on the pile shaft, which is right here. And then it's connected to the base plate.
Great, thank you, Aaron. For Gary, how can this be applied for four-legged tower supported on helical pile piers to take care of lateral loads?
There's a myriad of applications for the collar vanes. I know Dr. Gallant mentioned, the signage, and that's certainly been our focus related to the infrastructure focus of the study. But we see the collar vanes applicable to any type of construction where lateral load resistances are required, including self-supporting towers, mooring anchors, just pile foundations for structures, buildings, etc. So that's one of the things that we like about this, is that the collar vane itself lends itself to many different application options.
Perfect. We have a question: where is the study at in terms of durability? And I'll throw longevity in there too. Is it comparable to traditional foundation shafts?
You want me to go, Gary?
I think the question is related to service life or corrosion. Would that be a fair bet to make?
That's how I read it.
Okay. I mean, it is possible that, and we haven't done it yet with these samples, but it's possible we could galvanize these vanes, the collar vanes, so to add some additional resistance to, from corrosion perspectives. That is, I'll let Dr. Gallant continue, but that's certainly something we have to address on a specific basis on wherever the location is in terms of the soils and conditions of that particular site.
It's going to depend in part on the corrosivity of the soil that's there. Typically, this is protected through galvanization when we're dealing with steel. Gary mentioned that we're working on some things. We're working on other materials that would be more resistant to those types of conditions, similar to what I think has been put on some used for bridges around here. So we're kind of thinking about the same thing there from the composites perspective a little bit. There's potential for that to move forward this summer. I won't speak too quickly, but there's a long way to go there. So we've been moving fast. I want to see if we, I don't want to promise anything yet, but yeah, we're thinking about alternative materials as well. They are used all the, helical piles are used all the time, though. I should just say, for transmission towers and other foundations regularly. It's not system that way. So similar to other steel structures, I guess is the short answer.
Perfect. A question, many of these types of signs will have a breakaway coupling at ground level. Does the helical pile allow for a similar breakaway coupling to be installed?
That's a specific detail for sign structures, and there's no reason it couldn't be incorporated.
Yeah, we'd have to develop the product to accommodate that, and that is correct. A lot of transformer bases or T bases on poles have that. If you're looking at either for sign, well, the T bases are more for poles, but for sign structures, yeah, we'd have to certainly develop something that, and that hasn't been our focus, but yeah, it could be something we could work on.
I think the development of that would be relatively simple compared to that. So
Our next question is on soil types. I expect soil types will limit the ability to use helical piles, and likely the vanes with further limit use. Could you speak to appropriate soil types and limitations?
Soil types will limit the ability to use helical piles. Well, if you're there's limitations for every foundation type. Helical piles are, you're not going to be installing through cobbles and boulders. If you've got a really cobbly bouldery, soil type, this helical piles are not going to be a good option. All right. So that's, we can start there, and certainly that would limit the use of the vane. So that's one aspect that you would think about. And then everything else, really, when we're talking about, sands, all right, basically sands, clays, as we start to get finer grained materials in there, you should be able to use helical piles. Now, the size of the vane will depend on the size of the loads that you anticipate. And so I'll just use the loads that we've been talking about today, but it could be the wind loads, height of the sign structure, and things like that, for example. That would dictate really the diameter of the vane. All right. In addition, not just the loads, but then in addition to the strength of the soil that's available. All right. So the soil type will play a role, of course, in how large the vane would need to be. I hope that kind of addresses your question.
Perfect. A couple more here in the chat. With respect to corrosion, FHWA and AASHTO have corrosion recommendations for loss of section. Galvanization is not likely required. Just evaluation of loss in section. Do either of you want to touch on this?
I'll just say that's correct. Galvanization is usually a way to delay, or basically a way to extend the service life of a steel member. So you've got to eat through the galvanization first, and then you're going to start to get section loss as stated, and basically you'll typically design for the end life of the structure, right? Based on those corrosion estimates. So that's absolutely right. I think that's what we were alluding to, or attempting to state earlier when someone asked about durability. We didn't do a great job, so thank you for that.
And we actually have an audience addition to a previous question we have. We have installed square shaft helical piles through 6 meters of cobbles and small boulders. Pipe helical piles will have much more difficulty. So just wanted to throw that one out there. And our last two questions both have to do with something we've touched on before. But if you have anything else to add, please feel free.
I'll add one thing to that thought, and not necessarily on the fact that they could install, but they mentioned square shafts. We've tested this with square shafts, smaller diameter elements with the vane. What you end up seeing is that basically, if we're thinking about load deflection response and other things, you're going to get the same response no matter how skinny or wide the shaft, because the vane is by and large dictating the lateral performance. So this can be adapted and used for other shaft types. And the person mentioned a square shaft. That's a relatively small pile. That's readily used all over the place. So I just wanted to, it triggered a thought. I couldn't present everything today, but we have results that would show you everything looks the same regardless.
The vane's doing all the work when it comes to the shear and moment forces, and that's that's one of the nice things about it being versatile with respect to the helical piles themselves. So again, makes it adaptable to different applications.
Yeah, this isn't meant to be for one shaft type. Pile type. Sorry, Aaron, I'll let you
No,
go.
perfect. Thank you both for your thoughts on that. Our last couple questions both have to do with frost heave behavior. I know we've touched on that in a previous question, but if you have anything else to add to that, specifically, can you discuss frost heave issues with the collar vane?
I guess I'd only be repeating myself from before, and I think I just opened up the question. It looks like the person said thank you. I don't know if that was in response to the discussion we had about frost earlier. Yeah, I suspect it was.
Just by virtue of the two working together with the pile, the helical doing the work on resistance of that. I mean, that's I think the best answer at this point right now.
As far as it being pulled or pushed out of the ground, that the helices deeper in the ground, well below the frost depth, is what's going to prevent that any heave. There's no expectation that the whatever the helical pile collar vane system is supporting would
Perfect. Well, thank you both. That is all the questions we have, and we've just run up against our time. So with that, thank you all for joining us for the TIDC March webinar on improved helical pile performance with collar vane technology. Please join us this June for our next webinar on advancements in structural health monitoring by Professors Zhengwei Wang and Suyang Yu from the University of Massachusetts Lowell. Keep an eye out for registration for this webinar coming soon. And registration is now open for the TIDC annual conference happening this August 6th through 8th at the University of Maine Wells Conference Center. You can follow the QR code or the link on screen, and I will put that in chat as soon as this wraps up. And we'd love to have you up here in Maine in August to hear about all kinds of topics on transportation infrastructure durability. So if there are any questions that we weren't able to get to today, I encourage you to scan the QR code on screen or follow the link. This will bring you to TIDC's Contact Us page, where there's an option to select webinar follow-up. This will prompt you to enter a couple of pieces of information so we can get back to you, and then you can put in your question. And lastly, the recording of this webinar and certificate of attendance will be available at tidc-utc.org. That link will be in chat shortly. Thank you all and have a great afternoon.